some of the parts of this presentation assume some prior knowledge, for example, about SSIS or seismic attributes. You may have that, you may not have that. If you don't have that, don't hesitate to ask our panelists at any time during the presentation or ask me after the presentation. So before going into the technical part of this presentation, let me go over the contents, the structure of the presentation. I will start with some introduction about the steering cube and explain some fundamentals about how to calculate the steering cube. Then I will go into the backbone of our in-house workflow for steering cubes, creating a detailed steering cube and background steering cube. And I will explain a little bit about scale and the different kind of filtering options you can use for producing a detailed steering cube and a background steering cube. Then I will go over 3 applications of the steering. First, steering for structure-oriented attributes and filters, so steering to steer attributes or other operators with a step out along the seismic reflectors. Then steering for curvature and other dip attributes, so using the steering information as the information itself that tells you something about this subsurface. And finally, dip steering as input of SSIS. After those 3 standard applications of the dip steering, I want to show a few slides about the new application. We're working on developing dip steering on fault planes and doing filtering on fault planes. And after that, we have enough time for questions and discussions. So let me start with going over the basics of a steering cube. The first question, of course, is why build a steering cube, preferentially a very good steering cube? Well, the underlying reason is, of course, that the Earth is not flat. So the seismic image, which is a representation of that non-flat Earth, will contain a lot of dip information. If you extract that dip information, that is on itself a very valuable attribute. If you look at it, you can see a lot of very subtle features, either fine-grained subtle structural features or stratigraphic features. I will have some examples of that later in the presentation. Also, you can use it to steer attributes or filters that have a step out. So an operator that goes from the center trace to a trace to the north, to the south, to the east, to the west, to do that extraction not along a horizontal plane, but steer that extraction along the seismic reflectors and therefore be more geological correct in the attributes or filters that you're making. So all in all, using the steering as a component of your attribute workflows, you see more detail, you work more accurate, and you work more faster in your stratigraphic and structural interpretation of your seismic data. That is the basic advantage. So let's start. What is a steering cube? To avoid all misunderstandings, a lot of people who do a lot of structural interpretation associate dips with horizons, but we have here a volumetric measure. That is, the steering cube is present at every inline, crossline, and sample grid point in the seismic survey, except maybe for some padding on the edges where the operator length moves or eats up some data. It's a 2-component cube with an inline and a crossline dip in there. That is the mathematical way we store the data, and that's completely equivalent for a true dip or polar dip and an azimuth, as geologists are more used about thinking about dip information. And you can convert them in the attribute engine to a true polar dip or azimuth. The data is stored in physical units, meaning microseconds per meter. That is, if you move 1 meter in the inline direction or 1 meter in the crossline direction, it tells you how many microseconds you have to move up or down to stay on the same reflector. This is important to realize, because the first thing we often do in our OpendTect project is set up the project, and that includes a coordinate transform. And the second thing is often a steering cube, making a steering cube. Now, if you later find a mistake in your coordinate transform, the coordinate transform from x to y to inline to cross lines, and it will actually change your bin dimensions. For example, you calculated your steering cube at 12.5 meters per crossline bin, and it's actually 25 meters per crossline bin, and you correct that. That means then that your steering cube is off by in half, and that you have to recalculate that particular steering cube. But that's only if your bin dimensions changes after the calculation of the steering cube. It's just a handy thing to know. I did it wrong once, and let's share it so that other people don't make the same mistake. So this is, and I apologize for my drawing capabilities here, but this is the best representation of a steering cube as I could come up. You have reflectors in the seismic data, and at every grid point, inline and crossline grid point, and every time sample, you have two components, an inline and a crossline dip that represents the dip of that particular reflector. You can also visualize that in OpendTect. This is a little example with some nice structuring here, and you can overlay the steering cube you produced as a semi-transparent layer where the colors represent the direction of dip. Here the purple colors representing a dip to the left, the green colors representing a dip to the right, and on the cross line it's just opposite. And the more dense the colors are, the greater the dip. To show one of the reasons we want to do the steering cube, it's the quality of dip steered attributes. Here we use a dip steered similarity, which is a discontinuity attribute. I have here this red line on the foreground of that, on the viewer side of that red line. I calculate the similarity without dip steering. You see it has less resolution, it has less contrast between background and foreground, and where you have dips it goes sometimes completely wrong. While here on the side of the red line that's furthest away from the viewer, I use dip steering to correct the extraction of the trace pairs for the dip. I get a much cleaner image, I get much sharper discontinuities, and sometimes I avoid things that are just clearly wrong if you wouldn't correct for the tip of the seismic events. To recapture from my introduction, how is the steering used? The first use is as an attribute. One example is that is, for example, the curvature, where we calculate from the dips around a center point the amount of bending of the reflector. You can use steering to create structure-oriented attributes, that is, attributes that do have a step-out, and the extraction of those step-out traces are corrected for the dip using the dip steering. And for the same way, you can create structure-oriented filters where the filter operator is curved along the seismic reflector. It's important to notice there that we not only use the dip in the center point, but that we also do the dips, use the dips in the next traces. So it is not a flat dipping surface, it's really a curved surface that follows the reflector with pretty good accuracy. And finally, we use the dip steering as input for our SSIS plugin, which is another DHB plugin for stratigraphic interpretation. So you see, in-house, and I assume also for many of our users of our software, creating the steering is the first step in many different workflows, and that's why it's important to do it good. I will quickly go over the three algorithms that we use to calculate steering. I won't treat rigorously the mathematics that are involved behind it, but just go conceptually over the principles. We have three algorithms. The first one is Fourier-based, Fourier transform-based. The second is gradient-based, and the third one is event-based. For the FFT-based, the principle is that we extract a small cube. Typical dimensions are 3, 3, 3, inline step out, cross line step out, and time sample step out. And that small cube we will move through the data, first in time direction, in the second direction the inline direction, and the third direction the cross line direction. At every extraction point, so at every sample point, we transform the data to the Fourier or frequency wave number domain. Then in that frequency wave number domain, for every frequency we pick the maximum using a subsample interpolation. So it goes beyond the regular resolution. We fit a polygonal and take the maximum from that. And as we substitute the rule, wave number is slowness times frequency, and from that slowness is representative of the dip. That is the broad outline of how the algorithm works. If you want more mathematical details, I would like to refer you to our panelist Christopher, who is actually the designer of this particular algorithm in our software. Having done this and extracted the dip in the inline and crossline direction, the subcube moves to the next position, etc., etc. For all practical purposes, the important things you need to know about this is that the FFT-based algorithm is less sensitive to noise, but it's relatively slow. Compared to the next algorithm, the BG gradient algorithm, it's about 30 times as slow, so that's a significant difference. Yet we use it for particular applications, especially SSIS, where the noise sensitivity or the low noise sensitivity is really a critical advantage. Also, this option has the perfect option where we actually use some tricks to get that subsample interpolation even more accurate, and where we avoid some approximations in finding the maximum dip. It will give you a more accurate answer, but it will make it again a much slower algorithm. In practice, we do not use it that often in-house. The perfect option. Then the gradient-based algorithm, I first wanted to say that this is developed in collaboration with Andrew Wilson of BG. We actually has been a key factor in developing this, and together with BG we could produce this as a plugin in OpendTect. The principle is, again, we extract a small cube and we walk it through the data the same way. Now in every cube we calculate the instantaneous phase. Then we calculate the gradient on the instantaneous phase, and then the gradient vector is perpendicular on the seismic event. So if you know the gradient vector, you know the directions or the dip of the seismic events. Of course, there are some tricks in the algorithm to make this robust and stable, but I won't go into the particular mathematics behind that. And then again, having done it on one evaluation point, it moves to the next evaluation point until the whole data set is done. The disadvantage of this algorithm is that it's more sensitive to noise. You will always have to add a second filtering step to get rid of the noise, and that is called a detailed steering cube. However, the speed advantage is so much that even with that second filtering step, this is by far the fastest algorithm, and we use it for dip steered attributes and for dip attributes where we use the dip itself as an attribute. Then the last algorithm is the event steering. We use that not that often in-house, but I will still treat it for completeness. This one is trace-based, so it does at one trace, or actually a set of traces at one time. At that set of traces, it picks the peaks, the troughs, and or the zero crossings as surfaces. Those are locally fitted as a locally flat surface through the peaks, troughs, and zero crossings. And then the dip of these flat surfaces are determined. Of course, that leaves you with holes between the extrema in your trace, and those are fitted by interpolation of the dips between those flat surfaces. And then you go to the next trace and repeat this process. As mentioned, this is a little bit of stepchild between the three algorithms, and personally I don't use it that much. So that far for the real basics, the fundamentals. Now I will go to the workflow for the detailed and the background steering, which is really the central algorithm in making steering cube for the first two applications, dip attributes and dip steered attributes and filters. Why different steering cubes? Well, first, if you just would output a raw steering without any filtering using the BG algorithm, your output will be too noisy. So the detailed steering cube already has some filtering applied to it to remove noise. Then going to the background steering cube, the advantage of that is that you remove certain fine-grained structural and stratigraphic information in the dips, and doing that you can view at your information on different scales and with different resolution, and that has some advantages that I'm going to explain further deeper in the rest of the slides. This is an horizon-based example, so this is really to for you to get your head around the concept. In the top image here, and actually let me make my pointer visible all the time. Here in the top horizon, we see that I picked a horizon on a trough very accurately. We see some incisions where this formation has incised in the lower formation. Here applied a 15 by 15 averaging filter on that horizon, so it's a smoothed version. You see at the points of the incisions, it will not follow the exact timeline anymore. It will actually cut across those incisions. You see that also very clearly in the top view of the structure map. By the way, I would like to acknowledge the Nova Scotia Department of Energy who made this data publicly available. You can download it on the Open Seismic repository on the website opendetect.org/OSR together with some other publicly available data sets. So what happens if we display an amplitude-based display on the horizons? If I do that on a very accurately tracked horizon, so the detailed horizon, I do see those features coming back, but they're not that clear, they're not that much jumping out of them, and they're not visible everywhere. However, if I do the same thing on the smoothed horizon that has an average by average 15 by 15 filter, so the background horizon, I see in the amplitude extraction many of those features jumping out of me. They have the correct width, so that's a much better display of the geology. On the other hand, if I going to extract the inline dip, that is the dip going in this direction, and I extract the dip from the detailed horizon, I see many features. I see the outlines of those incisions very sharply displayed as positives and negatives depending on the side you are. Well, if you do the same dip extraction on the smoothed horizon, the background horizon, you can hardly find the location, any trace of those incisions being present. So apparently it does matter the amount of averaging you apply to which attribute displays better on a horizon. And that is the same principle for the detailed steering and the background steering. Some attributes, some filters work better with the detailed steering, some attributes, some filters work better with the background steering. And that's in part what I'm going to talk about in the next few minutes. So applying this to your whole seismic volume, how would the detailed steering cube look? Well, if you follow this reflection, it would very accurately trace the dips of every point of that reflector, which means that at the location of these faults where the reflector, the peak here, is still connected, it would actually trace the reflector over the faults, because we have here a connection of peaks. And this is one example. An other example that often happens is in low offset faults. However, if you put a big lateral filter on this information, what you're going to get is just the information of the background dip of the dominant dip present in the whole section. And that is the dip, for example, of this block and this block averaged. So we see that we follow the reflector pretty accurately still where we have layering, but then at the position of the fault, this dip will be the average of all these dips, and that will be still approximately in the direction of a regional dip. So it won't follow the reflector dip exactly at that point, and that is the critical point of making a background steering. We see when we use that significant differences in attributes created with the detailed steering and the background steering. For example, this is a detailed dip steered similarity. We see that at some points the similarity discontinuities are not registered at all on the detailed dip steered similarity, while they are present on the background dip steered similarity. While at other locations we see that there's a marked increase in signal strength using the background steering. So for this application, apparently the background steering is doing a better job. On the other hand, we can look at the dip as an attribute. We do that here by converting it to a curvature volume. And here we look at the most positive curvature using the detailed dips as an input, and we see very fine-grained field of faults here. We see here some noisy stuff related to salt movement deeper in the section. However, if we use the curvature using a background steering, we only see the major fault trends remaining. And actually what is interesting, that we now see the flexures in these layers caused by the deeper salt much more prominent. So playing with the different scales, we see different amounts of detail in this attribute, but we also see different geological features highlighted. To summarize this, the detailed steering cube will contain information about fine-grained stratigraphic and structural features of the seismic data. You should use it generally as an attribute, so polar dip, curvature, if you want to emphasize detail. However, you should use it as steering, dip steering for similarity attribute or filter if detail should be removed. On the other hand, the background steering contains information primarily about the background structure, the regional dip, and some major structural features such as major faults. You should use it as an attribute if you want to highlight only the overall high-level structure or stratigraphic features, but you want to use it as steering if detail should be emphasized. That might be counterintuitive, but that's how it works. So this is the most complete workflow of creating detailed steering cube and a background steering cube, including some unnecessary intermediate steps. But I will go over the intermediate steps because I want you to understand the whole process and the possibilities we have. We start with the seismic volume, then we calculate a steering cube using the PG gradient algorithm with a 1 by 1 by 1 step out, and that would typically give what I call a raw steering cube that we discard later. Because the gradient steering is too noisy, we always have to apply a medium filter for raw steering. Typically I use a step out of 5 samples up and down. The step outs are always defined in samples, not in time in OpendTect. What I would get from that is a detailed steering which is more or less noise free. So that is a final product I want to keep. Then here I apply twice a lateral filter that can be both a medium filter or an averaging filter in the inline direction and the cross-line direction. Typically you would again merge this step in one step, doing a 5 by 5 times 0 filter in the inline, the cross-line, and the sample direction. However, if you want to work with very large filter step outs, say this would not be a 5 step out for the inline but a 20, it is a possibility, though the quality of your workflow goes back a little bit, but it is a possibility to first filter in the inline direction and then filter in the cross-line direction to speed up the process. And typically I would use then a filter like that, 20 in inline direction, 3 in cross-line direction, and then here 3 in inline direction, 20 in crossline direction. Having done that, you end up with is a background steering, and that just contains information about the grand structure of the seismic data. Here are some images so you can see how that looks in practice. You have a seismic survey here, nicely folded in different grout fault blocks with synthetic and antithetic faults. This is the output of the raw steering, and typically you see some noise bands that are often associated with low amplitude, low signal to noise ratio layers, and you see singular spikes popping up. If I apply my vertical filter, I see that those bands and the singular spikes have been removed. However, I do see the fine-grained information of the dip registering the faults. In fact, I could do a very good dip interpretation on this particular fault interpretation, this particular dip volume. I see the fault here, I see 3 ones here. So this isolates the faults pretty good. Then I apply a lateral filter in this direction, and that is the output of that is the background steering. And the background steering, I mainly see the dips related to the regional dip in each fault block that is slightly rotated to each other. So we have some right dipping values here in green, and we have different left dipping layers here in blue. And the only fault feature I can with any certainty interpret on this is this major fault here. So I remove all my information about the detailed structure, I mean the fault structure in there. So the efficient structure, and I will pop out the presentation in a moment and actually show this in OpendTect. The efficient workflow here is go from seismic volume, calculate the gradient, calculate the vertical medium filter in one step, with as output product the detailed steering, then filter in the lateral direction, the inline, the crossline direction, and then get a background steering cube. So let me show in OpendTect where to find the buttons to do that. All calculation and filtering of steering is found under the processing tab in the menu. Steering, 3D, create. You select first a seismic input, then here you find the different steering algorithms. We use the BG fast steering. The calculation step out, the default parameterization 111 is almost always good. Then here I want to filter a vertical medium filter, so 5, 0 in the inline direction, 0 in the crossline direction. It's inline, crossline, and time direction. And just because this is an example, I will limit the range to one particular inline, and then you have to give it an output name. So this would be detailed steering using the BG algorithm. Okay, and then in practice you can submit it to a single machine or a multiple machine. You proceed, and it processes in batch mode. So in the same time you do have access to OpendTect. I already did this in advance, so this is how the output would look. I again put it in a semi-transparent layer on top of the seismic. Now always, though it's not very useful because you just see the dips and you see the faulting on the section, but I always look at the dip attribute as such on the section as quality control. I want to see if the noise is really out there and if the dips really represent my correct dips. You see, if you go, keep your eyes fixed to here. If I go over the volume, I see actually the dip value. This is a crossline dip displayed on the inline, so the dip from one crossline to another. I see the value down there, and I can potentially verify if that's the correct dip by the measurement tool here. Measuring the dip, then I see here the vertical distance in milliseconds and the horizontal distance in meters, and by dividing the distance by the time to a time difference, I can approximate the dip of these reflectors here, and I can see if my dip volume is approximately in the ballpark range. That is a good QC value method. Actually, let me clear that. So far creating a detailed steering cube. Then the next step would be actually filtering the detailed steering cube to a background steering cube. I go again to processing, steering, 3D, filter. Now, input steering data. I use the big steering here because I need to have some step outs. Again, we'll do it only on one line for this particular example. Then here, and this is available in the next stable release and in the current development release, we now have the choice between the filter type medium or average. In the lateral directions, I actually prefer an average, and I will tell you later why. And then we create a background cube from this. Again, as a batch process, so we have access to OpendTect in the same time. And the output of that looks like this. So where you saw before in the detailed steering, a lot of fine-grained information related to the faulting in the deeper section. Here we only see the information, actually the dip information related to the actual layering, the structuring of the reflectors. So that far as processing this in OpendTect. Let me switch back to my presentation, and from current slide and go further with the explanation of this. As you saw, I already used now the average operator for the lateral filtering. I can do that strictly for the workflow creating a detailed steering cube and a background steering cube, but I could take it one step further and then make a very background steering cube, so to say, with, for example, an average filter not by a 5x5 but a 15x15 step out. And with that I start seeing features on significantly different scales. Here this is the output of a curvature attribute, the maximum curvature, so I display the largest principal curvature of the two curvature directions, which is the very large maximum or positive or negative value, depending if you have concave or convex bending of your surface. So this is the original, just a detailed steering cube. This is after applying a 5x5 averaging filter to the steering. You see that it's essentially the same data minus some fine-grained noise, but most structures that I find here, I find back here, minus some fine-grained, mainly noise, and with a little bit less resolution. And if I take the next step and apply a 15x15 average filter on my detailed steering, I really start seeing only the big regional fault and fracturing structures in my data. So then I start really to look at the next scale up of geometrical information. Some thoughts on the parameterization. The default parameterization in the previous examples are usually pretty good. So usually you can go ahead, but you shouldn't stop thinking. First of all, you should always display after creating the steering cube on the section view in a semi-transparent value if it's not noisy, if there are the accurate values. But also there are some situations where you want to think about your parameterization, especially the parameterization of your filters, or if applicable of the FFT operator. And that is if you have very low frequency content data, if you have very steep dips, if you have on 1 or 2 millisecond time sample rate, or if you have a depth survey, you have to take account of that anyway, and very small bin sizes. And usually it means that you need to increase your sample step out in time direction, or your bin step out in the lateral directions a bit for your operators. And I always encourage people not to think in actual sample and dip step outs, but think about, especially in time direction, how much of the wavelength of the dominant wavelength your operator is capturing. So normalize your thinking to the dominant wavelength of the seismic data. Then a little note on the median versus the average filter in the lateral direction. This is the inline dip of a certain survey after a median 5x5 survey filter. You see that there's still significant acquisition footprint left. While if I do the inline dip after an average 5x5 filter, I see that I can still see an imprint of the acquisition footprint, but I see all those diagonal features coming out much better. So the imprint of the acquisition footprint is far less after an averaging filter compared to a median filter. And this is the same image again for the maximum curvature, and we see the same thing. We see some very heavy imprints of the acquisition footprint on the median filter background steering, while the averaging filter background steering is a little bit more well behaved there, but loses some resolution. That is, by the way, you can see that very nicely that you lose some extra resolution. And that is because of certain characteristics of the filter. A median filter de-spikes very well, but it retains steps, which is often a good feature, for example, if you filter over faults. And it retains some periodic features. The disadvantage of that it is sensitive to letting an acquisition footprint pass. The averaging filter, on the other hand, smooths. It leads to lower resolution, and it's sensitive to outliers. But the smoothing makes sure that the acquisition footprint is often better suppressed when you apply it in the lateral direction. So in the vertical direction, where we really want to de-spike those noise spikes and those noisy layers, I would recommend using the median filter. In the lateral direction, I would use the averaging filter. So that is the main workflow for creating a detailed steering and a background steering. So now I want to move on to show some applications of the steering. And I would like to start with using the dips truly as steering. That is for structure-oriented attributes and structure-oriented filters. First, I will show an example of the dip steered min similarity. That's a discontinuity attribute, and conceptually that works like this. If I'm at the discontinuity here, I will take a trace pair to the left, and I will take a trace pair to the right over a certain time window and compare how similar or dissimilar they are. So what happens if I use the detailed steering and I want to do this at this fault position? I'm going to use very accurately the dip of this reflector, and I will extract one trace pair up here following the dip, and I will extract another trace pair down here following the dip. If you see, I can remain centered around the reflector, and there will actually be not much difference in those trace pairs. So my similarity will not register this fault using the detailed steering. However, if I do the same experiment with the background steering, I will have here the dip of my regional layering despite the reflector going down. I will extract the trace pair down here using this dip. I will extract the trace pair, the other trace of the trace pair up here using the regional dip. If I compare the trace segment extracted down here and the trace segment up here, they will be very dissimilar. So the similarity attribute will register that fault. And you saw this image before. In all practicality, you see a marked increase in your similarity or any other discontinuity attribute with a step out using the proper background dip steering. So for sorry for this header, this is the wrong header. It should say dip steered similarity there, but for dip steered similarity, the background steering is the way, is the right steering to use. Then here now we go truly through the dip steered median filter. We have the same problem there. What we will do with the dip steered median filter is make a three-dimensional flat filter operator that follows the reflectors and takes the median value of all amplitudes found on that operator. It's normally step preserving. That is, if I have a median filter that sticks out to something and there are 2 values from here and 3 values of here, and the center point is here, it will generally preserve this step here. However, especially if I have low offset faults, what will happen with the detailed steering, I will actually shape the reflector through the same reflector on both sides of the fault using the detailed steering, and it will start smoothing over the fault plane. So that is not what we're intending to do. In the background steering, my operator will just ignore the fault and will actually behave in the right step preserving fashion. This is a little example of that. This is a dip stirred medium filter applied 2 times to the same section. Here with detailed steering as input, and here with background steering as input to steer the operator around the reflectors. You see plenty of points here, 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 and here where the detailed steering actually connects reflectors over the fault where they shouldn't be connected. Here is very clear. So also for dip stirred medium filters, the background steering is the correct steering to use. And I would say for 99% of the cases where you use steering, the dip volume, the dip steering volume as steering itself, you want to use the background steering. The other ones are more for academic use. Some thoughts on using the steering cube on low signal to noise seismic, or workflow that we use there often is to make what we call a second generation steering cube. First, we create the background steering on the original seismic, or what I often do is take a low pass on the original seismic, trying to remove preferentially the high frequency part, which often has most of the noise in it. And since I want to create a background steering cube anyway, I'm not interested in the high frequency features that much anyway. So then I create a background steering cube from the original seismic. Then I apply a dip stirred medium filter to the original seismic, which is a great despiking filter. I get a neater image of the original seismic that is relative noise free. And then I apply the workflow for the detailed steering cube and the background steering cube again on the filter to clean seismic data, and I use that for every subsequent process, and that subsequent process can be creating a curvature volume, it can be creating a similarity volume, it can be doing the dip stirred medium filter again on the original seismic, but now with a better steering cube. So you can iterate the procedure twice if you have very bad data. So now we'll move to attributes calculated from the dip itself. We'll do that at the hand of a little demonstration in OpendTect. We'll show you the dip, the value of variance of the dip, what you can do with lateral derivatives of the dip, vertical derivatives of the dip, and finally a curvature example. Let me move back to OpendTect. And here I will open my attribute engine and actually show you how to build those attributes. The attribute engine can be accessed via the icon attribute 3D. The first thing I'm doing there is extracting, in this case, the polar dip for my detailed steering, and later we'll do it one more time for the background steering there. Then you use the dip attribute, you select the right steering data, and as output you can choose the polar dip, but you can conceivably also choose azimuth. Polar dip is the true dip of the reflector as geologist thinks about dip. Azimuth is the direction of the true dip. You have the inline dip, the crossline dip, and you can also do an apparent dip, which is the apparent when you have a surface cross-cutting the volume in a certain direction. So that is what the geologist would see in an outcrop. This polar dip we put in a variance statistic, so we use the volume statistic attribute there, input that polar dip that we extract, and we can orient it very vertically, as here, with a low step out. So I have a little subcube here that's -50 to 50 seconds large, milliseconds large, and a step out of 0, 0 that's going to run through the data, extract data at every sample point, and then within the subcube it will output the variance of all the dips found in that subcube. I don't use any steering here, and I call this the vertical variance of the polar dip. Then one more step I took here is actually because the vertical variance is a quadratic measure. It has a very large dynamic range. I put it in a mathematics attribute and I did an ln, a natural logarithm on the data. And the advantage of that is that I bring it back to a range of like 1, 2, 3, an order of magnitude range. So let me show the results there on this particular section. This is the result. I have to go out of the attribute engine real quick to make it semi-transparent. So we see that we pick up the gas chimney here, but we also pick up plenty of other things, and that is one of the reasons that we use this as an attribute in our neural network gas chimney attribute set. The same way we can do the volume statistics on a more flat-oriented operator. Here I use a time gate from 0, 0. I use a step out of 6, 6, again taking the variance, and now I use central steering of the background steering cube to approximately shape the operator along the regional dip. And actually, I forgot to tell, the variance of the dip is a very good measure for the amount of chaos in the data. So if you have high variation in your dips, you have relative high chaos in your seismic data. So it's an attribute for gas chimneys, for mass transport systems, slumps, that sort of seismic signatures. And here I see that if I use a more lateral oriented operator, I get actually an excellent view of that gas chimney. So this would probably be the better gas chimney attribute. And also I see 3 levels of attribute values here: low, low, high, and in the middle. And when I analyze that, I see that the high values here are associated with this hummocky facies that has undergone dewatering and polygonal faulting and some slumping as a result of that. The low values are associated with parallel and semi-parallel high amplitude layering, and the intermediate values are associated with the sigmoidal structures in this diatelic sequence. So with that, this chaos attribute is also an attribute to discriminate between different facies. And in the upper part, it also highlights very nicely wherever I have disturbance through channeling or other incisions in the seismic data. So that is an example of using the dip to emphasize chaos. You can also emphasize morphological features. You can do that by putting the gradient into, or putting the dip attribute in a gradient attribute. Always use the convolve attribute for that. In the convolve attribute, you put the polar dip detailed as input in there. There you have different options, and one of the options is the pre-width gradient filter, which has gradients in different directions. And you can calculate that and display it, for example, on a horizon to see morphological features, especially dip-related morphological features. And here's an example of that. This is all marine formations. The paleo coastline is probably somewhere here. We have waves of sand fields pseudo-parallel to the coastline, and then we have some channeling that has incised in the deeper part of the basin. Well, both channel incisions will give a dip signal on both sides of the incision of the channel, and the sand waves also are strongly geometrical defined features with a dip landward and a dip basinward. So if we take a lateral derivative of that, such as the inline gradient of the detailed polar dip, we see very clearly the morphological features jumping out. Oh, I'm sorry, I used the crossline dip here in this particular view. This is the inline dip view. So it does matter which direction I take the derivative from they are slightly different, and I can actually recombine them again using the mathematics attribute. Here, squaring them and then taking a square root of them, and that will give me an absolute value for the amount of change at a particular site. So we see some paleo meandering going here for some revert channels. We see here, if you look right, some tributaries coming from this steeper section coming together and feeding into this channel. So this is a very powerful attribute for analyzing phases that are defined by geometrical dip characteristics. You can also use that derivative in the time direction. Here I do the polar dip again, but now for the background dip I do then the time gradient in the pre-width filter. And if I take the time gradient of the dip, I'm going to see something very interesting for stratigraphic analysis. I'm going to see at which locations my dip changes in the vertical direction, and that are often locations that you have angular unconformities. When you see on-lap like here, when you see truncation and different off-lap patterns here. Let me flip that on and off. And here you see the boundary between a wedge drape and some sand waves right under it. So if you apply the derivative in the vertical direction, you have an attribute that more or less approximates your lapping patterns, and it might be very helpful to identify your angular unconformities and system traits in your data. Final attribute I want to talk about is the curvature. Again, that is a very powerful attribute. It takes the dip steering as input. You can do it multi-scale as they're demonstrated. The most useful curvatures are maximum, minimum curvature. Maximum curvature is the maximum. Largest principal curvature. The minimum curvature is the weakest principal curvature and is actually an attribute for fracturing. Then you have the most positive and the most negative curvature, which registers concave and convex structures. I will show one particular Z-slice here with these attributes displayed. This is the most positive curvature displayed of a detailed dip. You see very fine-grained faulting patterns in this section. You see again a fracture sections through upcoming a salt wall defined here. And this is a time slice where we actually slice through different formations. This is a formation that is subjected to dewatering and shows polygonal faulting. I can also display that on another scale. This uses the background steering, so this is filtered. Now I only see the larger scale faulting, and what now really jumps out of me is the outline of that salt wall that is pushing up these sediments, deforming the sediments that are on top of the salt wall. And these are the equivalent images, but then with the maximum steering, where I see the convex and the concave structures both in the red and in the blue values. Again, the background showing only the large scale faulting, and then the detailed steering showing fine grained faulting, the polygonal faulting, and these structures. So that's as far as what you can do with the dip as an attribute itself. Let me move on to the PowerPoint. Next subject will be dip steering for SSIS. SSIS is a plugin we developed for sequence stratigraphic interpretation to make that a more automated procedure and a more digital procedure. I realized that not everybody is familiar with it, so I will go 4 slides giving a quick introduction in that. We do it currently on 2D sections or 2D lines and 2D transects through 3D data First step is to map the major boundaries in your seismic data and to define your area of analysis. Second step is to calculate the current stratigraphy, which is basically a very dense grid of horizons, including stratal terminations. And that's an automated step, so that doesn't require much user intervention. Then the third step is using the current stratigraphy both in the structural domain as what we call the Wheeler domain for interpretation. In the Wheeler domain, we flatten the data, so the vertical axis becomes a relative geological time. The horizontal axis is an axis from landward to basinward. These are flattened current strats with stratal terminations. So this place where I have sedimentation at a certain relative geological time. On the landward side, I have erosion hiatuses. On the basinward side, I have condensed sections. And I can use the trans-ICMO Wheeler diagram as well as the current stratigraphy to make a complete system project interpretation. So that is the philosophy behind this plugin. Where does the dip steering come in? That is in the creation of the current stratigraphy. The current stratigraphy is directly derived from the dips. So you have a dip volume and you start tracking horizons from that dip volume. So you start typically at a fixed part of a section. Your starting point typically spaced with the seismic sample rate, so 4 milliseconds would be a very typical value. Now from every point you're going to use the dip to track the horizon from your starting position to the next trace, to the next trace, to the next trace. You do that also for the next starting point under that. As you already saw when I took the vertical derivative of the dip, not all the dips are vertically aligned parallel, and especially when you have angular nonconformities, they either diverge or converge very quickly. So we use that by, if there's a lot of convergence, to terminate horizon tracking, terminate horizons, and when there's a lot of divergence, we'll insert new horizons. Then that way we implicitly map the angular nonconformities in this workflow, but we can only do that when we have a good steering available. So the objective for this is to create the dip steering to calculate the current stratigraphy. We want to be, for this, as accurate as possible, so we don't want any noise. So as a consequence, we'll leave the BG gradient method here, and we use typically the FFT method. We can then use more or less or none filtering in the lateral and vertical direction. The advantage of unfiltered dip is we see more detail, which gives you more information, but can also be confusing. The advantage of a filter dip is that the Wheeler deep domain might become easier and more easy interpretable and will lead to a little bit less confusion. So let me show some examples of that. This is the current stratigraphy as we get it from an FFT 3.3 step out for the FFT parameters, 3 in the line direction and 3 in the sample direction. And we do no filtering at all. You see a very accurate image of the current stratigraphy. However, because we have all detail, you will have a lot of points with divergence or convergence, and you see that some current strats have very short length. Here you see the same thing with a white background, and there you can indeed see that some current strats are quite short. When you move that to a Wheeler domain, that leads to a lot of variation in your movement. Progradation, retrogradation follows each other quite quickly. That may even be very valuable if you do fine scale interpretation. For example, on a reservoir level, you want to see where there are potential barriers to flow, etc. You want to see if two sands between two nearby wells are actually connected or not. However, if you want to do a more regional interpretation, that might lead to extra confusion and system effects that you cannot correlate over a large extent of your data set. So here I followed the Fourier transform dip creation with an average 3x3 filter. You see already that still all the current stratigraphic horizons are more or less following the reflectors. However, you see that the average length of the current stratigraphy has increased markedly. So it's a little bit more stable, robust procedure. And what you see already when you have a white background is that you see the surfaces where you have a lot of on-lab or top-lab going on. You can identify them quite easy. Actually, you could identify a number of geobodies quite easy already looking at this display. So this is for interpretation, maybe a little bit less confusing. Those geobodies you can identify are also visible in the Wheeler domain. Again, for example, in this falling stage, I have a number of events within the falling stage which are probably individual geobodies in that complete falling stage. So you can still have a pretty accurate interpretation. Then I applied a 9x9 averaging filter on the FFT, and what you see is that the resulting chronostratigraphic events really start running away from the actual reflector values. And that is a problem. You might have seen it in lesser extent here, but the real quality criterion here is if the angular unconformities where you have your boundaries are still at the right position. That's the ultimate thing for secret stratigraphic interpretation, not if you have followed horizons with 100% accuracy. But here, they're completely off. I also see that if I display this with a white background, that I filtered so much that the areas of convergence and divergence really have disappeared. I really cannot identify that much geobodies anymore here. And you see that in the Wheeler domain, a lot of detailed information actually has been meshed together. So on the SSIS, the conclusions would be the amount of average, definitely not too much. Rather have too few filtering and have a little bit more information there than to remove meaningful information. The second consideration is, what is your scale of analysis? Do I want to see like flow barriers in a reservoir formation, or do I want to correlate multiple system tracks along a subbasin or a basin? And the third is a little bit of personal preference. Do you like to see all detail, or do you like to see the big lines between the system tracks? So that are the considerations, but I would in practice take any amount of averaging with some experimentation between maybe the 0,0 and the 3,3 averaging filters I showed. So those are the three regular workflows that I can imagine a lot of people are actually using. I want to give some insight in a new workflow we're working on. That is actually extracting the dips from fault planes and then using them to align filters along the faults. So this is something that we're experimenting in-house on, and this is something that maybe can be replicated by power users right now. I will go over the main steps, and if you have detailed questions, you can. I'm more than willing to go into detail in a later one-on-one discussion. So the first step is to go from a seismic volume to a dip volume that actually contains the dips representatives of the fault planes. You see here that the fault planes dipping to the left are represented by blue colors. Fault planes that are dipping by the right are represented by green colors. And when I have just seismic data, I have very low fault data. So in a number of steps, we achieved here that we can display the dip of the fault in a bulk volume, in a dip steering volume. Then subsequently, we can use that to apply structure-oriented filters, either medium filters or averaging filters, along the fault planes. That has two advantages. First advantage is that the staircase behavior of the typical discontinuity attributes disappears. So I get a true continuous dipping attribute. The second advantage is that the original attribute often has gaps, and those gaps seem to disappear after filtering, so I get more continuous fault planes. So this is definitely already an attribute that would be easier to deal to use when doing fault interpretation, because it looks more geological and it's more continuous, like you want to model your fault as continuous entities. The second application is blending this more continuous fault with a dip-stirred medium filter that's very smooth, and then use it in 3D auto tracking of horizons, where we use the smooth dip-stirred medium filter Seismic to track horizons seeded in each individual fault block, and then we use this continuous fault or discontinuity attribute as a fault representation as barriers between each fault block, avoiding that the 3D auto tracking will inadvertently move from one fault block to another fault block and fill the next fault block on the wrong horizon level. So this kind of hybrid tracking volume is another part of this experimental workflow. And this would be the typical result. You see the seeds in each fault block. You see that each fault block is auto-tracked till that fault plane, and then terminated along the fault plane. And then subsequently, you can triangulate the gaps between the faults again to get a full horizon. So that was the fundament about how dip steering works, how to create detailed dip steering and background dip steering, what are the considerations there for your filters, showing some applications of dip steering and dip steered attributes and filters in dip attributes and for SSIS, and some novel applications we're working on. Before moving on to the questions, I would like to acknowledge the DGB development team who made the dip steering algorithms, implemented them, implemented the attribute engine. Thanks to this excellent team, we can do these things. I want to thank my colleagues of the DGB project team for developing these workflows as a group, as a team. And finally, I want to acknowledge Andrew Wilson of BG for collaborating with us on the gradient steering algorithm. So I would like to give the word back to Renee and move on to the questions and discussion section of this webinar.
All right, well, thank you very much, Friso. I think you gave us quite a bit of information, and for those who either arrived late or who just want to go back and watch the webinar to get more information, it will be available in 2 days. It will be available online on Friday, and we will send out the link, so you will be able to have that. And also, I would like to request in that same email, we will send out a feedback form that's going to be about 5 questions long, and that will help us to improve the webinars to come. So if you wouldn't mind taking a couple of minutes to fill that out when they do come in. Now we'll go ahead and move on into the question and answer session, and at this time I'm also going to go ahead and unmute our panelists, and I will leave it up to them to mute themselves so we don't hear lots of extra noise, but that way our panelists can chime in if Friso chooses, or if they would like to add something else. We've had quite a good group here today, and I'm sure there are going to be a lot of questions ready to come. One person actually typed in a question, and if they do not want to ask that question, if they want to remain anonymous, I will start asking the question for them, and if they would like to ask the question themselves, then you know who you are, and you can go ahead and raise your hand or type the question in to the questions pane. And everybody else, if you have questions, either raise your hand or type a question into the questions pane. So the question we'll go ahead and get started with is dealing with rules of thumb for dealing with very high frequency data, 1 millisecond sampling, steep dips. So, and I actually have the hand raised, so I will go ahead and unmute the asker of this question. You have the floor.
Yeah, hi Friso, Rainer speaking. It's Statoil in Calgary. Yeah, I'm working in the oil sands, and we have got shallow data and very high frequency data and high sampling rate, 1 millisecond sampling, frequency-wise up to 180 hertz, and steep dips to image. Well, these are the channels which I want to image. So do you have any rule of thumb for creating the best steering cube for that? Because when you were discussing it, you said, well, if you have some anomalous data, you have to play around. Yeah, sure, I'm doing that. But on the other hand, do you have any experience so that you can give me some guidelines?
Well, what I can say there is that when you increase your sample rate, you would typically want to use larger windows, but you say that you also have very high frequencies. So that might compensate it. What you want to do is capture, say, at least half a wavelength, preferentially a wavelength of your dominant frequency in your data. So you can just measure how long your dominant wavelength is. I say that will be 20 milliseconds or 30 milliseconds. Then you know with 30 milliseconds, if I have a 4 millisecond sampling, I would capture it if I use an FFT algorithm with step out of 3 times. So that will be 7 samples times 4 is 28. That will approximately capture the whole wavelength. However, I have a step out of 2. I would have to have twice as much step out, because then I would need step out of 6, which gives 12, 13 times 2 is 24 milliseconds operator, which is the same magnitude of that. So if you want to use the FFT algorithm, you will have to do that. However, if you have high frequencies seismic data and your dominant frequency or your dominant wavelength is only 15 milliseconds or 10 milliseconds, you might be good with the default parameters again. With the BG algorithm, you're mostly good with the 1 by 1 by 1 to calculate your dips itself, though it will be noisy. And then you will have to do the same adjustments on your subsequent vertical median filter. You will have to increase that. Typically, that median filter should be also a half to a complete wavelength, dominant wave period long. So the best rule of thumb I can give is to measure your dominant period in your data, whether in time data that's a period, in depth data that's a wavelength. Move back to your sample rate and see how much samples in the vertical direction you actually need to fill that. Does that answer your question?
Okay.
Rainier, does that answer your question?
Yes, it does. Thank you very much.
Okay.
Friso, this is Gert. Maybe you can explain a little bit more about why you use the cross-line dip on an inline and vice versa. Because I've seen a lot that people are confused by the terminologies inline dip and cross-line dip, and maybe you can explain when you make a steering cube how you QC your steering cube and why you use an inline dip.
Yes, I
or
can.
Or cross-line and vice versa.
I can explain that. Let me actually move out of the presentation and go to OpendTect to do that. Let me clean this up one moment. And here I do have a crossline and an inline, but it's the wrong one. Yeah. So Geert's question is, why do you display a crossline on the inline and the inline dip on a crossline? And I should have explained this actually in the session itself, but in OpendTect, the crossline dip is defined as the dip going from one crossline to the next crossline. So that is the dip I would see when I'm face on with an inline, because this is the first crossline, this is the next crossline, and the crossline dip gives me the dip going from one crossline to the next crossline. Similar when I face on with a crossline, I would have to display the inline dip, because the inline dip tells me what kind of dip or what kind of value I need to go from one inline to the next inline and end up at the same reflector. So from one trace here to the next neighboring trace. That is the reason you want to display the crossline dip on the inline and the inline dip on the crossline. As far as QCing then, I unfortunately don't have a raw steering available here, but I conceivably could create one real quick. Let me do that. I go to process and steering.
So if I just see on this steering cube is that you really see that you don't have a lot of very dark colors, and there's not really a lot of spickles in there. Normally when you see a raw steering which is not filtered enough, you'll see there's a lot of outliers, small little patches of very dark colors. And if you see that, a display like this will immediately show that. And so therefore, when you make a steering cube, the first thing you do is display it like this, that you have your seismic and grayscales, and on top of that, in semi-transparent, you show on the inline you show the crossline dip, and then you look at whether you see outliers. When you see too many outliers that is not corresponding to a geological or seismic event, then you know that the steering is not filtered correctly. And therefore, I think this display is, here you see it immediately. You see a lot of these little dots, and in fact, these dots are not corresponding to a fault or not corresponding to a seismic event, which you just see that these are outliers. And now you can see that these are this steering cube is not filtered correctly. So then you know that you have to go back and do a better job. And just to show you the difference between a good steering cube and a bad steering cube. And this is a very good QC process.
Yeah, just to show you, just applying that vertical medium filter will lead to this. So you see that actually some of those things are related to little faults, but the display going from here to here, this is a more accurate display of the seismic data, where you have removed the extremities and the instabilities in the steering algorithm. Renee.
Yes, Friso.
Any other questions?
Yes, actually, I passed along a question to you in the questions pane.
Okay.
I'm not sure if the asker wants to ask you himself or just have you answer the question. Well, the question is, can you elaborate on why event steering is not used much? He says, well, as a trace can be reconstructed almost perfectly from its peaks and troughs, is there not a lot of redundant calculation in other methods?
Well, for myself, the answer would be I always use the BG steering in particular applications where I need to be very accurate FFT steering. In those accurate applications, I would always keep using FFT steering because it has certain advantages and doesn't have any ambiguities when you, for example, have a splitting point, when you have an on-lap, etc. As far as why I use mainly the BG steering is that it's partly habitual. It works fine, it works good, and I don't have the same experience with the event steering. I never do that detailed QC or benchmark between those. However, Geert might have some more comments about it because I think he has experimented more with this particular steering.
Yeah, but I think you're right. For me, it's basically the same. The first results were not that encouraging, and indeed the current algorithms are doing a pretty nice job, and they're pretty powerful. So, and that's the reason why we never went into great detail about this particular steering. But so pretty much the same.
Okay, well, if that question was sufficiently answered to our asker, then I guess we can move on, and if not, if you would please raise your hand or reply to another question in the questions pane. Do we have any other questions? Well, okay, if that is the if that's the end of the questions, then I would like to thank the people who did ask the questions, and thank you very much for participating. And everybody else, thank you for joining us in this webinar. And Friso and our panelists, thank you all very much for helping out and doing a wonderful job today. So if we have no other questions, I'll leave just a moment longer. Or do any of the panelists or Friso have anything else to add?
No, the only thing I would like to extend to all people, if you have a question later, or if you have a question that would be a more detailed technical discussion, you can always reach us via the support or info email addresses of DGB, and I'm gladly to discuss things further in a one-by-one setting. And of course, thank you all very much for the attention.
Okay, well, thank you everybody for joining us, and I hope you will join us next month. We will send out an announcement. Actually, I'll try to pile everything in one email so you're not inundated with tons of emails, but please join us next month where we will be talking about survey setup in different areas. And also, please join us at the SEG in Denver. We're going to be having training, both introductory training and advanced topic trainings held before the SEG in Denver, as well as the first user meeting to ever be held in the U.S. We will be holding that the Sunday that the SEG starts in Denver. So for any of these things, please go to our website, email us if you have any questions, and hope to see you next month. Thank you all for joining.